Imagine this. A colossal star, millions of light years away, suddenly explodes in a cosmic spectacle that outshines entire galaxies. For centuries, humanity has been captivated by these fleeting bursts of brilliance known as supernovae. But here's the catch. These events are so unpredictable and short-lived that studying them in their earliest moments has always been nearly impossible. Until now, a groundbreaking new protocol promises to change everything by detecting supernovae just hours after they explode, giving astronomers a front-row seat to one of the universe's most dramatic performances. Supernovae erupt without warning, appearing as dazzling flashes in the night sky where nothing seemed to exist before. These explosions mark the violent deaths of stars, and they serve as natural laboratories for understanding the life cycles of celestial bodies. Yet, because they happen so abruptly and unpredictably, scientists have historically struggled to observe them soon enough to gather meaningful data. But thanks to cutting-edge sky surveys that continuously scan vast areas of the heavens with unprecedented frequency and precision, astronomers can now detect supernovae almost daily. But here's where it gets controversial. Is simply detecting supernovae enough? Not quite. To truly uncover the secrets behind these cosmic fireworks, researchers must act fast. The key lies in capturing detailed spectra, essentially the fingerprints of light emitted by the explosion, as early as possible. This is critical because the first few hours and days after a supernova's initial flash hold clues about what caused the blast and how it unfolded. Enter Lluís Galbany and his team at the Institute of Space Sciences, ICECIC, in Barcelona. In a recent pilot study published in the Journal of Cosmology and Astroparticle Physics, they introduced a revolutionary methodology designed to obtain the earliest possible spectra of supernovae. Their goal? To analyze these cosmic blasts within 48 hours or even 24 hours of when the first hint of light reaches Earth. And guess what? They succeeded. So why does this matter? Well, supernovae come in two main flavors, each tied to the mass of the star that gave birth to them. Thermonuclear supernovae occur when relatively small stars, those with an initial mass no greater than 8 times that of our Sun, reach the end of their lives. Before exploding, these stars evolve into white dwarfs, ancient stellar remnants held together by quantum forces. If such a white dwarf resides in a binary system, it might pull material from its companion star. Over time, this added mass increases internal pressures until the star becomes unstable and detonates. On the other hand, core collapse supernova involve much larger stars, giants weighing more than 8 solar masses. These behemoths shine brightly due to nuclear fusion occurring deep within their cores. However, once they've exhausted all fuel sources and can no longer produce energy through fusion, their cores collapse under gravity's immense pull. This triggers a catastrophic chain reaction, culminating in a titanic explosion. The distinction between these two types isn't just academic. It shapes how we interpret the universe itself. Early observations provide vital insights into the nature of the progenitor systems, helping refine theoretical models and estimate crucial parameters like mass, composition, and environmental conditions. The sooner we see them, the better, emphasizes Galbany, underscoring the urgency of rapid response protocols. Historically, snagging data so quickly was a pipe dream. Most supernovae were spotted days or weeks after the fact, leaving gaps in our understanding of their earliest phases. But modern wide-field surveys have flipped the script. By repeatedly scanning large portions of the sky, these surveys enable discoveries mere hours after an explosion occurs. Still, having advanced technology isn't enough on its own. You also need clear guidelines for using it effectively. Galbany's team tackled this challenge head-on, testing their protocol using observations from the Gran Telescopio de Canarias, GTC. Their study focused on 10 supernovae, split evenly between thermonuclear and core collapse varieties. Impressively, Most were observed within 6 days of their estimated explosions, while 2 were caught within 48 hours, a remarkable feat given traditional timelines. Here's how their protocol works. First, they identify potential supernovae candidates based on 2 criteria. The candidate must not appear in previous night's images, and it must be located within a galaxy. Once both conditions are met, the team activates the OSIRIS instrument on the GTC to capture a spectrum. Spectra reveal invaluable information, such as whether the original star contained hydrogen, a hallmark of core collapse supernovae. Armed with this knowledge, researchers can then correlate their findings with other datasets, including photometric measurements from tools like the Ziki Transient Facility, ZTF, and the Asteroid Terrestrial Impact Last Alert System, ATLAS. These additional checks help paint a fuller picture. For instance, unusual patterns in brightness curves might suggest interactions with nearby stars in binary systems. Cross-referencing multiple observatories' data ensures accuracy and depth in analysis, given their success in obtaining data within 48 hours. Galbany believes even faster observations are achievable. What we've just published is a pilot study, he explains. We now know that a well-coordinated rapid-response spectroscopic program paired with deep photometric surveys can realistically collect spectra within a day of the explosion. This breakthrough paves the way for systematic studies of supernovae during their infancy stages. Upcoming projects like the LaCilla Southern Supernova Survey, LS4, and the Legacy Survey of Space and Time, LSST, both located in Chile, will build upon these foundations to unlock deeper mysteries of the cosmos. And this is the part most people miss. While the science is undeniably exciting, it also raises questions worth debating. Should we prioritize speed over thoroughness in astronomical research? Could focusing too narrowly on early-phase data overlook important long-term trends? What ethical considerations arise as global collaborations grow increasingly reliant on shared technologies? Now it's your turn. Do you think rapid response protocols represent the future of astronomy, or do they risk overshadowing slower, more deliberate approaches? Share your thoughts in the comments below.